Can't I use AI to just summarize? No, dude. You need to at least know how to. You need to know how to read things. Like, you need a basic understanding of how to get through things. Like, somebody puts a paper in front of you and he's like, "Oh, I just summarized this documentation. Can you like read through it? Tell me what you think." And you're like, "I forgot how to read. AI just tells me everything." The purpose of a container in the standard library cannot be to provide the optimal solution for all scenarios. Inevitably, in the fields such as high-performance trading or gaming, the optimal solution within critical loops will be a custom-made one that fits that scenario perfectly. However, outside of the most critical of hot paths, there's a wide range of applications for more generalized solutions. Hive is a formalization, extension, and optimization of what is typically known as a bucket array container in game programming circles. Similar structures exist in various incarnations across high-performance computing, high-performance trading, 3D simulations, physics simulations, robotics, server-client applications, and particle simulation fields. The concept of a bucket array is you have multiple memory blocks of elements and a Boolean token for each element which denotes whether or not that element is active or erased, commonly known as a skipfield. If it is erased, it is skipped over during iteration. When all elements and blocks are erased, the block is removed so that iteration does not lose performance by having to skip empty memory blocks. That's actually a bit inefficient. That's actually a bit inefficient to have a Boolean field. You're having another byte of memory effectively for each item in the container. So that's not good. So I think this paper optimizes that. The advantage of this structure is as follows. Because a skip field is used, no reallocation of elements is necessary upon erasure. Because the structures use multiple memory blocks, insertion to a full container also do not trigger reallocations. That's important. A vector triggers a reallocation when it's full. This means that element memory locations stay stable and iterators stay valid regardless of erasure or insertion. Do the iterators stay valid here? Do the iterators stay valid in vector? They don't. They don't. Right, so only Hive does. This is highly desirable, for example, in game programming, because there are usually multiple elements in different containers which need to reference each other during gameplay, and elements are being inserted and erased in real time. That's a mess if stuff get invalidated. How did only half get the... Yeah, this is kind of sad. But that's why you go on getcracked.io. This question's free. You learn, right? The whole point of this channel is to learn new stuff. Problematic aspects of a typical bucket array are that they tend to have a fixed memory block size, do not reuse memory locations from erased elements, and utilize a Boolean skip field. That's what I mentioned before. It's kind of not that great. The fixed block size and lack of erased element reuse leads to far more allocations and deallocations than it's necessary. Given that allocation is a costly operation in most operating systems, this becomes important in performance-critical environments. The Boolean skip field makes iteration time complexity undefined, as there is no way of knowing ahead of time how many erased elements occur between two non-erased elements. That's true. You can have a million, you can have one. You don't know how many. This can create variable latency during iteration. It also requires branching code, which may cause issues of processors with deep pipelines and poor branch prediction failure performance. Now we get to what a hive is. This is where you learn about the hive mind. Okay? A hive uses a non-Boolean method for skipping erase elements, which allows for O1 memory, amortized iteration, time complexity, and more predictable iteration performance in a bucket array. It also utilizes a growth factor for memory blocks and reuses erased element locations upon insertion, which leads to fewer allocations and reallocations. That's actually kind of interesting, the growth factor. So you might start off with a block of 10 that can fit 10 items, and then the next block you allocate is not going to be another 10-item block. It'll be a 20-item block or a 30-item block. Because it reuses erase element memory spaces, the exact location of insertion is undefined. That's cool. In most implementations, it's likely, for performance reason, that unless no erasures have occurred, or an equal number of erasures and insertions have occurred, the insertion location would be at the back of the container. That makes sense. Because if I have 3 things, let's say I have 4 things. Beginning, end. I erase this, where am I going to put the next item? I'll just put it back at the beginning, the first slot. The container is therefore considered unordered but sortable. Lastly, because there's no way of predicting in advance where erasures may occur during iteration, an O1 time complexity square bracket operator is not necessarily possible. That's right. So there's no random access, but it is bidirectional. Which other data structure is bidirectional but not random access? Interview question, go. First person that gets it gets a treat. Yeah, Trevor's right, stood list. There are two patterns for accessing stored elements. The first is to iterate over the container and process each element. The second is to store the iterator by the insert function, or a pointer derived from the iterator. That makes sense. Okay, insertion to back. The following images demonstrate how insertion works in a hive compared to a vector when size equals capacity. Vector, original memory block full, newly added object. Original block and new object copied to a newly allocated block twice the original size. Colony. I think that's what he means by hive. Original block is preserved and linked to a newly allocated block which doubles the current size of colony. New object is stored in the new block. The following demonstrates how non-back erasure works in hive compared to vector. Original memory block, delete this item. In a vector, everything gets shifted over. So when somebody asks what is erasure in vector, it's worst case O of n. Why is it worst case O of n for vector? It should be easy by looking at this chart. Somebody in chat, why is vector erasure O of n? Yeah, if you erase at the front, you need to shift everything over one. Now imagine you have an object you need to copy because it can't be moved, and you have thousands of them. That's a massive performance hit. So these are the sorts of things you should be thinking about when somebody says, oh, like a game is not optimized or whatever is not optimized. It's because people make poor decisions about the data structures they use and how they use those data structures. Colony. Original memory block. Erased element is noted in the skip field and added to the memory block's free list. Will be reused the next time an element is inserted. There's additional introductory information about the container structure in the CPP talk, though some information is out of date. Motivation and scope. I don't think motivation is that important. An example is a typical video game engine. Most games will have a central generic entity or actor class, regardless of their overall schema. Entity actor objects tend to be a has a style object rather than it is a style object, which link to, rather than contain, shared resources like sprites, sounds, and so on. Those shared resources are usually located in separate containers, arrays, so that they can be reused by multiple entities. Okay, so we have like a human entity, and I'm not a game dev, so correct me if I'm wrong. We have a human entity, and they have a object, which might be a pointer to or a reference to maybe an array. And that array might contain sound files or pointers to sound files. And so we have that shared resource that multiple different human entities refer to. So that single array of sounds can be used by multiple different humans. Entities are in turn referenced by other structures within a game engine, such as quad trees, oct trees, level structures, and so on. Entities may be erased at any time. For example, a wall gets destroyed and no longer is required to be processed by the game engine, so it's erased. A new entity is inserted. For example, a new enemy is spawned. While this is all happening, the links between entities, resources, and superstructures, such as levels and quad trees, must stay valid in order for the game to run. The order of the entities and resources themselves within the containers is, in the context of a game, typically unimportant, so an unordered container is okay. Unfortunately, the container with the best iteration performance is a standard vector, loses pointer validity to elements within it upon insertion and pointer index validity upon erasure, which is what we just spoke about here. This tends to lead to sophisticated and often restrictive workarounds when developers attempt to utilize vector or similar containers under the above circumstances. Stood lists and the like are not suitable due to their poor locality. That's right, because nodes are allocated in desperate locations of memory, which leads to poor cache performance during iteration. This is, however, an ideal situation for a container such as a hive, which has a high degree of locality. Even though that locality can be punctuated by gaps from erase elements, it still works out better in terms of iteration performance than every existing standard library container other than dec or vector, regardless of the ratio of erased to non-erased elements. As another example of particle simulator, okay, we're probably not that interested in particle simulation. Design decisions. So this is how you become more cracked if you're interested. If you're not interested, you can watch a cat video, but this is how you become more cracked. You read like the way that these people think, because these people that design these data structures, they've gone through 1,000 bad designs before they've come up with one really good design that they're proud of. The three core aspects of a hive from an abstract perspective are a collection of element memory blocks plus metadata to prevent reallocation during insertion, as opposed to a single memory block. A method of skipping erase elements in O1 time during iteration, as opposed to reallocating subsequent elements during erasure. That's a good idea, and I think that's where the metadata is going to come in from. I think that's where the metadata effectively exists. Because there's no point of looking at an element and saying it's true or false. If it's true, don't skip. If it's false, skip. And doing that all the time. Instead, you should probably just allocate a piece of information that tells you maybe how far in advance to skip. So instead of going iterating 1 plus 1 plus 1 plus 1 plus 1, you do like plus 4. You just skip to the next index 4 above. An erased element location recording mechanisms to enable the reuse of memory from erased elements in subsequent insertions, which in turn increases cache locality and reduces the number of block deallocation. Blah, blah, yeah, that makes sense. Each memory block has multiple elements. The metadata about each block may or may not be allocated to the block themselves. This metadata should include a minimum, the number of non-erased elements within each block, the block's capacity, which allows the container to know when the block is empty and that needs to be removed from the iterative chain. So this is really related to what Python does with the Python memory manager with pools, arenas, and blocks. A non-Boolean method of skipping over erased elements during iteration while maintaining O1 amortized insertion time complexity is required. Finally, a mechanism for keeping track of elements which have been erased must be present. We get that. If you want to become a more cracked dev, you read this paper and you try to build it yourself. And you're going to probably build this and realize like, okay, that was a bad decision. Go back. Okay, continue. That's how you get good. A lot of people ask me, how do I become a better developer? It's not by just walking through a tutorial with some guy holding your hand and telling you type this on your keyboard next, kids. It's read a paper and say, how can I implement this myself? And then you're like, oh, okay, well, maybe this is a good implementation, a bad implementation. You run it past your friends, run it past my Discord, etc. Okay. However, the implementation of these is significantly constrained by the requirements of the container. Lack of reallocation, stable pointers to non-erased elements. Yep. Original reference implementation. Ooh. This is the secret sauce. Ooh, interesting. So remember I said that instead of having a Boolean, which the paper says we shouldn't have, we should probably have details that tell us how many more indices to look forward of? This is what it's doing. Now, somebody in chat tell me, why is this 2 and this is not 0? NMNML got it right. It's bidirectional, right? So in the forward direction, we skip 2. Skip this, skip this. When we iterate backwards, we will still want to skip 2. Skip this, skip this. Look here. This middle one is 0. Why is this middle one 0? Why isn't this also 3 or whatever? This is how you want to start thinking when you're thinking about implementation and also when you're thinking of like questions you might get in an interview. Middle one will always get skipped over. That's right. You'll never read that field. You'll never read this 0. Here he talks about the reference implementation. This is essentially a doubly linked list of group structs containing a dynamically allocated element memory block metadata, and dynamically allocated skip field. Yeah, this is the powerful structure. How does bidirectional work? Let me show you. See this? Block 1, block 2, block 3. When you go past 4 elements in this example, essentially what you're saying is I need even more space. So we're not going to allocate another 4 memory location block. We're going to allocate an 8 one. We're going to double the next block we allocate. Same thing here. If we exhaust all these slots, we're going to allocate another memory block that has double the space. And when you call .begin, you're getting an iterator to the first element of the first memory block. When you call end, these were erased from the end. So you get 1 past the last element. That's what end always does. It's 1 past the last element. So you get 1 right here. And then you can iterate backwards or forwards. Unlike allocators, there's no option to specify new capacity limits in the move copy constructor. However, this makes sense for move constructors because specifying limits would cause the constructor to throw if the transferred block did not fit into the new limits. If the user wants to specify new capacity limits without copying from another hive, They do so with the following instead of calling a copy constructor. Interesting. I think hive limits, I think what this is referring to is the, we'll keep reading. I think what that's referring to is, and I think he mentioned it later, is the minimum and maximum amount of elements that each block can contain. I'll need to read, because reshape, right? Reshape, we'll look at that too. A method of skipping erased elements in O1 time during iteration. Okay, this is, I think, what I mentioned at the very beginning, and that's what we saw. Jump counting pattern. This effectively encodes the length of runs of consecutive erased elements into a skip field, which allows for O1 time complexity during iteration. Since there is no branching involved in iterating over skip fields aside from the end of block checks, it can be less problematic computationally than a Boolean skip field in terms of CPUs that don't handle branching or branch prediction effectively. The pattern stores and modifies the run length during insertion and erasure with O1 time complexity. It has a lot of similarity to the high complexity jump counting pattern, which was a pattern previously used by the reference implementation. Erase element location recording mechanism. There are two valid approaches here. Both involve per memory block free lists, utilizing the memory space of erased elements. The first approach forms a free list of all erased elements. The second forms a free list of the first element in each run of consecutive erased elements. I think pointing to 1, pointing to 2. Oh, sorry. 1, 1, 2, 3. So you have a linked list whose nodes are this, the first one of these two, and the first one of these three. The second one could be more efficient, but requires a doubly linked free list rather than a singly linked free list. The reference implementation currently uses a second approach, using 3 things to keep track of the erased element locations. Metadata for each memory block includes a next block with erasures pointer. Yep. So if I'm here, my next block with erasures pointer is going to be here, block 3. The container itself contains a blocks with erasures list head pointer. These are used by the container to create an intrusive doubly linked list of memory blocks with erased elements which can be reused for future insertions. Metadata for each memory block also includes a free list head index number, which records the index within the memory block of the first element of the last created skip block. Let me read that again. Free list head index number, which records the index within the memory block of the first element of the last created skip block. Okay. First element of this is the last created skip block. So I think it would be pointing to here. The memory space of the first erased element in each skip block is casted via pointers as 2 index numbers. The first giving the index of the previous skip block in the memory block, the second giving the index of the next skip block in the sequence. In the case of the head skip block in the sequence, a unique number is used for the next index. This forms a free list of runs of erased element memory locations, which may be I need to read that again. The memory space of the first erased element in each skip block is casted via pointers as 2 index numbers. The first giving the index of the previous skip block in the memory block. The second giving the index of the next skip block in the sequence. Let me take a look at this picture. Cast element memory space to record locations of previous next nodes in the free list of runs of erased elements for reuse during insertions. Okay, take a look at this. This guy's reusing memory that is allocated for objects to store numbers of indices. 255 means that there is no previous erased element, while 8 says the next erased skip block's head is at the 8th index. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's pretty cracked. That's pretty cracked. And then this one here, to the previous head of the head of the previous skip block, which is index 2, 0, 1, 2. Okay. Wrong? What am I wrong about here? A value of numeric limit skip field type max indicates the free list in the previous node is the free list head in the previous node in the free list. What am I wrong about the explanation here? 255, the maximum, specifies there is no previous skip field, so we can't have a value for its index. 8, which is not the max, states that the next skip field's head is at the 8th index. I want to understand hive limits a little more. Hive limits. Okay, here. The function updates block capacity limits in the hive and, if necessary, changes any blocks which fall outside of those limits to be within those limits. For this reason, it may trigger an exception with non-copyable movable types and also invalidated pointers, iterators to elements. This is dangerous then. Reshape. If you care about like pointer invalidation. The order of elements post reshape is not guaranteed to be stable in order to allow for optimizations, specifically in the instance where a given element memory block no longer fits within the limits supplied by the user. Depending on the state of the hive as a whole, the elements within that memory block could be reallocated to previously erased element locations in other memory blocks, which this is probably a beast to implement. This you need to think about this real hard. Additionally, if there's empty capacity at the back of the last block in the container, at least some of the elements could be moved to that position rather than reallocated to a new memory block.
Tomer, I have a question if it's okay.
Yeah, what's up?
So does that reshape actually uniformly make those blocks the same again? Is that what it does?
No, what reshape does is you pass in hive limits, which have a minimum and a maximum. So I think what that means is the minimum and the maximum amount of elements in each block. So if I was to say the minimum is 4, and the maximum, let's say here, I don't know how many there is. I think this is 16, and the maximum is now 10. Well, then I have a 16 allocated block here. I need to now shave the 6 off the end. I've allocated space for 6 more than I need. So now I need a 4th block that has 6 elements. Does that make sense?
Okay. Yeah. So then why are the blocks themselves, as I see it in this example, different?
Oh, because good question. What happens is this also happens in vector. So when you allocate a vector for like has 2 items in it to start, and you add a 3rd item, it doesn't just add, it doesn't just find and allocate a new memory block with 3 items or with a space for 3 items in it. It doubles in size. So it allocates a memory block with 4 items in it, and it copy or move constructs the original 2 items from the original memory block. Why does it do that? Because by growing the vector and growing a given data structure, what you're telling it is, I need more space. And the more space you demand from it, the more space it'll give you. So it's essentially like an exponential increase in the amount of space that it will allocate for you. So the next block, if I was to fill up all of block 3, the next block, effectively, it would allocate 32 items in that block. Because by constantly asking for more space, it's saying, well, okay, you really want more? Here's a lot more. And then you say, I want even more than that. Okay, oh, here's an even bigger chunk.
Okay, so how do we change that factor? And I guess that factor is bounded by the limits, the hive limits.
Yeah, so I that's what I believe the hive limits are specifying here. That's my understanding. I may be wrong, but that's my understanding. But in vector, you can't actually do that. That's not exposed to you. But in here they are. So hive is constructed with that in mind. So see here, see right here, this constructor.
Yeah.
Hive limits. So here you're telling it in its construction what its bounds should be. But in vector you can't do that.
We didn't specify its scale factor.
That's right. You don't know what the scale factor will be. So it might start off with 10, the minimum, if 10 is the minimum. It might start off with 15. You're just bounding the block size. But you know that once you've hit a 50 item block, it's never going to scale higher than 50 items. So you're effectively just going to have more 50 item blocks.
Okay, and I had a follow-up question in regards to the skip field, or like the element, how it reuses the elements to say where the pointer is to the previous section and to the previous index and the next index.
Yeah.
So right now, it's using, for example, in that in the example that's there, it's like 255 and 8,
Yeah.
right? And obviously that could fit in a short because it's like, two 8 bits together, etc. It's fine.
Yeah.
But what if you had the elements were very small in the sense that it was a short, but the capacity is very large, so it would need more bits to store where the next index would be.
So this is so pointers in 64-bit architecture, they're always 8 bytes, right? So what they're saying is they're going to reinterpret cast for elements that have been erased. This memory space, they're going to, and the first 4 are going to be the previous element index, and the next 4 are going to be the next element index.
So the elements here are actually the pointers to the actual elements in the heap. They're actually not the storage elements themselves.
I think so, because what it said here is... Let me just check again. Yeah, it says the memory space of the first erased element in each skip block is reinterpret casted via pointers as 2 index numbers. The first giving the index of the previous skip block in memory, and the second giving the index of the next skip block. I mean, when you think about it, because all these items are on the heap, you're storing pointers to items. So now you're going to be reinterpret casting the pointers to the items of the erased blocks to integers.
Okay. Yeah, that makes sense. I was just thinking the elements themselves was the storage elements of, for example, the object or the type that you put in the hive.
Yeah, this is like pretty nifty to use the space of erased elements as indices for the next erased element in the desperate list. That's pretty
Yeah, sorry for derailing.
No. It's a good question. People are probably asking that too. I use C++ and I never even knew this was doable. Yeah, well, it's good that you're in this call. This get iterator is kind of cool. Because hive iterators are likely to be large, storing 3 pieces of data, current memory block, current element within the memory block, and potentially current skip field node, a program storing many links to elements within a hive may opt to dereference iterators to get pointers and store those instead of iterators to save memory. This function reverses the process. Why does that save memory? Because a pointer is the size of a memory address, which is 8 bytes in 64-bit system. But in an iterator, we need 3 pieces of data, and each piece of data might be in itself 8 bytes. So we'd have 24 bytes of data in an iterator, whereas a pointer is just 8 bytes. So what we have here is this function reserves the process, giving an iterator, which can then be used for operations such as erase. So we give, this is pretty brilliant, we give a pointer to the element pointed to by the iterator, to the getIterator method, and it returns us a constructed iterator or a wrapper around that element. Is active. Interesting. This function tests whether it points to a non-erased element. First, you must check the memory block the iterator points to is part of the hive's current blocks. It could be a block that has been deallocated. Otherwise, checking the skip field might trigger an out-of-bounds exception, as the block might have been deallocated. There you go. I think we could directly use the skip field's pointer, iterator skip field pointer, to check erase, non-erase elements in question. Let me ask you guys this. Let's say that you are pointing, you have an iterator that points to a valid block. Given this structure, how can you check whether it's been pointed to an erased block? This is actually a hard question. I thought it would be easy. It's actually hard. So you have an iterator, right? It might be pointing to this. It might be pointing to this. It might be pointing to this. How would you implement an isActive method to know whether or not it's pointing to an erased block? And can you do that in O1 time? No, you don't have a bit that represents something as free. This implementation doesn't use a Boolean skip field. The skip field here tells you how many indices, forward or backwards, you need to skip. The issue here is, you might say, oh, well, that's easy. Check the skip field and make sure it's not 0. Then therefore you know whether the element there has been erased. But this one here in the middle has a skip field of 0 because you never actually iterate over the element, so it doesn't need a number. This guy's saying he's doing some pointer magic. He can reason whether or not the element's been erased via pointer comparison. The thing is, if skip field isn't 0, you know for sure that element's been erased. That might be like a basic check. So if it's not 0, I know it's been erased. Not 0, I know it's been erased. Hey, it's 0 though. So how do I know if it's been erased or not? In this example, it's erased. I can't just rule out that it's not erased. But this guy's saying he does some crazy, I don't even know what he's getting at, but he's doing some crazy pointer math. He's saying the reference implementation uses over-aligned, stood-aligned story. I've never used this. Pointers and iterators. And bitcasts them to relevant pointer types upon dereferencing, which get around the C++ standards concerned with reading values of pointers to erased elements. The pointer comparison used in these functions are between the over-aligned pointers, which while they point to the same memory space, critically do not point to the same type as the actual element which has been constructed there. Yeah, I actually don't get this. I'll be honest, I don't get this, how he's implementing that. Splice. Whether X's blocks are transferred to the beginning or end of this iterative sequence or interlaced in some way is implementation defined. Better performance may be gained in some cases by allowing the source block to go in front rather than the back, depending on how full the final block in X iterative sequence is. This is because unused elements that are not at the back of the hive's iterative sequence will need to be marked as skipped. And skipping over large numbers of elements will incur a small performance disadvantage during iteration, compared to skipping over a small number of elements due to memory locality. Oh, during iteration. Okay, I get this. Sometimes you need to read things 100 times. Okay. What he's saying is that, let's say that block 3 was totally full. And block 3 belonged to a different hive. So it was block 1 of another hive. So we have 2 hives. The first hive has block 1 and block 2. The second hive has its own block 1, but in this case it's block 3. Let's assume that this block 3 had everything full. Okay? When you're iterating, you don't want to be doing that too much calculations regarding the skip field metadata. You want to blast through it quickly. And something it's easier to blast through if there aren't erased elements in it. So you'd rather put the block with a lot of non-erased elements in the front. Oh, this is actually pretty interesting. So resize. There's no resize. This is a conscious choice to avoid confusing the user, as insertion location into a hive is undefined. In this case of hive, resizing would not necessarily insert new elements to the back of the container like it would in vector, when the supplied size was larger than the existing size, because new elements could be inserted into the erased element's memory location.